I will speak about Dirichlet and Steklov eigenvalues. I will recall my notations soon. And more precisely, I'm interested in optimizing these eigenvalues with a diameter constraint. So it's not exactly isodiametric inequalities, but it's more precisely trying to minimize or maximize these eigenvalues when I put a diameter constraint on the domain. So this is a work in collaboration with young people that you can see on this slide. And as usual, this is all these young people who make the job, and I just follow them. Okay, so my notations. First of all, since I am in a seminar where people are used to work in differential geometry, I prefer to be clear. I will stay in the Euclidean case. So my domain omega is not a manifold. It's an open set, bounded open set, or Lipschitz bounded open set in Rn. And I denote by lambda k the Dirichlet eigenvalues, so of my domain, and also by sigma k the Steklov eigenvalues. So for the Steklov eigenvalues, I need some regularity for the domain in order to have a discrete spectrum. I do not follow the same convention that Rick introduced recently, because for me, the first trivial eigenvalue is sigma 0, and sigma 1 is the next one. Okay. And so as I said, I am interested in minimizing the lambda k or maximizing the sigma k, because it is a good extremal problem with some geometric constraint on the domains omega. So I will recall quickly what happens when you put a volume or a perimeter constraint, but I am more interested here in this talk by a diameter constraint. Okay. So for lambda k, when you look at the minimization problem with a volume constraint, so you are minimizing lambda k with a volume constraint on the domain, it's well known that the minimizer of lambda 1 is a ball. This is the so-called Faber-Krahn inequality. It is well known also that the minimizer of lambda 2 is a union of two identical balls. This is referred in the literature by the Hong-Kran-Zege inequality, precisely because the three mathematicians discover or rediscover this property, which is quite easy to get just by considering and rearranging the two nodal sets of lambda 2 and using Faber-Krahn inequality for each nodal set.
Sorry, Antoine.
Yes.
I just want to make sure, were you still meant to be on the first page of your presentation?
No, I moved, so wait a minute. I have to. Okay. So you see the page introduction here.
Yeah, now I see the page introduction.
So it was just to recall my notations: lambda k for the Dirichlet eigenvalues, sigma k for the Steklov eigenvalues. And I was recalling what is known for the minimization of the Dirichlet eigenvalues. So the minimization of lambda k, first with a volume constraint, which is a classical problem, the problem most people have considered first. As I said, lambda 1 is minimized by the ball, lambda 2 is minimized by the union of two balls. And people were also interested in getting a general existence result for the minimization of lambda k. And it has been obtained in 2011 by Doreen Bucher on the one hand, and Dario Mazzoleni, Aldo Fratelli on the other hand, by two different techniques. And they prove existence of a minimizing set, which is actually a quasi-open set. It's not known whether it is regular and even open or not. And of course, many numerical simulations have been done. And in particular here, you can see the optimal shapes obtained numerically for the 15 first eigenvalue. So lambda 1, it's the disk, it is in the plane here. So lambda 1 is minimized by the disk, it is Faber-Krahn. lambda 2 by 2 disk, it is Onkran-Zege. Lambda 3 seems to be minimized by the disk, but it is still a conjecture to prove that the disk minimizes lambda 3 in the plane. The union of two different disks whose ratio are in the ratio are the link to the first zeros of Dirichlet of Bessel's functions here seems to provide the minimizer of lambda 4. And then after lambda 4, you have shapes which are no longer disk or union of disk, and it has been proved actually by Amandine Berger, who was a student of Edouard Houdet and Bruno Colbois. So you have different shapes, whatever they are, and just people are a little bit surprised and interested in the shape which minimizes lambda 13, which is this one, which appears to be non-symmetric. While we expected that shapes will always be symmetric, this is not the case. Okay. Now, if we look at the perimeter constraint, it turns out that the problem is simpler with the perimeter constraint. In particular, when you look at the plane situation, taking the convex hull of the domain instead of the domain itself, you see that the eigenvalue decreases and the perimeter also decreases. So if you put, instead of a quality constraint, you have to put an inequality constraint here. You see that the shape, the optimal shape has to be convex for free. And so existence is much easier to prove when you have a convexity of the shapes, because you have more easily continuity of the eigenvalues and so on. So for to be brief on that topic, lambda 1 is still minimizable because it's just a combination of Faber-Cahn inequality with isoperimetric inequality. The case of lambda 2, we looked at this case with Doreen Bucur and Giuseppe Butazzo a couple of years ago. We get in the plane an optimal domain which is analytic. And it's not the disk for sure, because it has 2 points where the curvature vanishes. These are the 2 points where the nodal line hits the boundary. Since the optimality condition involves the curvature at the gradient of the eigenfunction, you see when the gradient of the eigenfunction is 0, the curvature has to be 0 in some sense. And more generally, Guido De Filippis and Bojidar Velishkov have proved existence in any dimension for any case, and C1 alpha regularity of a minimizer for this problem. So you see that it is simpler than the volume constraint, because here you have regularity of the minimizer. There is also a paper by Vandenberg and Iversen where they prove some qualitative properties. And last but not least, Bucur and Freitas studied the sequence of optimal domains. So you have an optimal domain for any k, and you could be interested in what happens when k goes to infinity. Can you prove that the optimal domain has a limit? I will come back to that fact later, because it's an important question in that context. Okay, so in my talk, as I said, I want to consider a diameter constraint. So I want to minimize lambda k, the kth Dirichlet eigenvalues among domains in Rn with a diameter less than a constant d0. It's even simpler than the perimeter case, at least for the existence question, because here we can prove one more time that we have convexity for free, and moreover that the convex bodies are what we call convex body of constant width, because you want the diameter constraint to be saturated in any direction in some sense, otherwise you extend, and by extending you get something which is lower. So since you are minimizing, you want the diameter constraint to be saturated in any direction, which gives you this so-called convex body of constant width. Obviously, for k equals 1, the ball is still the minimizer because it's a consequence of Faber-Cahn inequality. Here, for those who are not familiar with bodies of constant width, I give a plot of 3 of them. The disk is, of course, a body of constant width. The famous Henrot triangle, which is obtained by plotting 3 arcs of circle on an equilateral triangle. And on the right, you have the same for a pentagon. So you have the regular Reuleaux pentagon. You have, of course, many irregular Reuleaux pentagon, which are still bodies of constant width. And even if it is not completely intuitive at the beginning, so a body of constant width, by definition, is a convex body for which the width, which is a distance between two supporting planes, has to be the same in any direction. And if it is counterintuitive, actually there is many bodies of constant width, and a way to see that, and we will come back on that later, is to consider the so-called support function of a convex body, which is the distance between the origin and the supporting plane, and call h this support function, and you can characterize bodies of constant width as convex bodies for which the support function satisfies this functional equality, h of theta plus h of theta plus pi in dimension 2, for example, is equal to the distance, to the width. So you see that you have many such function h. Just imagine that you are expanding h in Fourier series. Then you see that any function h whose even Fourier coefficient are 0, except the first one, will provide a convex body of constant width, if this is a support function. So you have many of them. Okay, so let me come back to that question of asymptotic behavior. The question is, okay, for any k, we have an optimal domain, say omega k star. What happens when k goes to plus infinity? Does my optimal sequence, my sequence of optimal domains converge? Actually, it turns out that in the case of a volume constraint, this question is open. We do not know whether omega k star converge to something. It's plausible, it's a conjecture that it converges to a disk or to a ball. And I say it's an important question because it's linked with the famous Polya conjecture, which claims that, okay, look at the Weil's asymptotic. Can you prove that the Dirichlet eigenvalues are on the right of the Weil asymptotic, while the Neumann eigenvalue are on the left of the Weil asymptotic? If you can prove that the sequence of optimal domains for the minimization problem converge to a ball, in some sense, to check Polya conjecture, at least in the high regime, for large values of k, it suffices to check the Polya conjecture for balls, and then to have some quantitative estimate. And since the Polya conjecture holds true for balls, you will have at least the Polya conjecture for high regime, I mean for large values of k. With the perimeter constraint, the question is easier, and as I said previously, Doreen Bucher and Pedro Freitas were able to prove it in the plane, to prove that the sequence of optimal domains converge to a disk. And in our case, with the diameter constraint, it's even simpler, since we are able to prove that the sequence of optimal domains converge to a ball in any dimension. So when I say converge, it can be, for example, for the Hausdorff distance, but since we are dealing with convex domains, actually any notion of distance topology on sets are equivalent for convex domains. So we are able to prove this convergence result. And let me give the proof, which is quite simple here. So let me denote by B D0 the ball of same diameter. I am working with a diameter constraint which is D0. And first, we have to prove that the sequence of optimal domain does not degenerate to a flat convex set. Since the diameter is fixed, it might happen that the sequence of domains shrinks to a convex set of lower dimension. So it can be done using either the Lie inequality and Weil's law, or even here, since we are dealing with bodies of constant width, we see that we cannot converge to something flat. Then, by the classical Blaschke selection theorem, we have a sequence of convex domains. There is the subsequence, it converges to some open convex set omega infinity for the Hausdorff distance. And the diameter is not continuous in general for the Hausdorff metric, but in the class of convex sets, the diameter is continuous. So you can claim that the diameter of the limit set is also equal to D0. Now you use the definition of the Hausdorff convergence. If you enlarge a little bit omega infinity, if you take omega infinity delta, which is something slightly bigger than omega infinity by considering the Minkowski sum with a small ball, by definition of the Hausdorff convergence, you know that omega k star is included into this enlargement of omega infinity. Then you use monotonicity of the Dirichlet eigenvalues. You know that lambda k of omega infinity delta is less than omega k of omega k star, which is the optimal value. And so by minimality, it is less than lambda k of the ball. Now you use Weis' law. And the Weis' law involves the volume of the first domain omega infinity. You forget the domain which is inside because the sequence of domain is moving. But you just look at the first and the last terms in this inequality. And Weis' law implies that the volume of the ball is less than the volume of omega infinity delta. And this is true for any delta, actually. So the volume of the ball is less than the volume of omega infinity, but the two domains have the same diameter. So they have to be equal by the isodiametric inequality. So you have proved convergence of the ball, right? Okay, so the next question is, okay, can we have an idea about the optimal domains in general? And is there any reason for which the disk could be the optimal domain for lambda k? So here, just for convenience, I'll fix the diameter to be 2 in order that the unit disk in the class of competitor. And do I have some reason to believe that the disk is the minimizer for any k? And at the beginning, we were more or less thinking that it could be the case. Because, first of all, as you have already seen, the disk is the minimizer for lambda 1. When we performed some numerical simulation we did with Benny Bogosel, we have seen that the disk seems to be the minimizer for lambda 2, lambda 3, lambda 5, lambda 5. And moreover, it's easy and we'll come back point easy to see that the disk is always critical to minimize. Cancel the first derivative, the first shape derivative. Nevertheless, it's not the case. The disk is not the optimal domain for any k, and more precisely, the following theorem gives a precise list of eigenvalues for which the disk could be the global minimizer. At least it is a local minimizer. So this list is the following. You have lambda 1, 2, 3, 4, 5, as I said. Here, lambda 6, for those who know the eigenvalues of the disk, you see that it is the first radial eigenvalue corresponding to a radial eigenfunction after 1. So you see that lambda 6 is not in this list. The two next eigenvalues are double eigenvalues and are in this list. Lambda 9 and lambda 10 are also indexes for which the eigenvalue are double, but they are not in this list, and so on. So you have a precise list of 17 eigenvalues for which the disk is a local minimizer, and for all the other eigenvalues, all the other which are not in this list, we can prove that the disk is not a local minimizer, right? So it's a little bit surprising. How can we prove that? It is just a local analysis. The idea is to perform some perturbation of the disk, and it's more convenient to stay in the class of bodies of constant width. So this is the reason why we make perturbation using the support function. So I recall here in this slide, what is the support function of a convex set? It is, as I said previously, the distance between the origin and the supporting plane in the direction theta. So for example, it's the plane because here I am the plane. We can identify in some sense a class of bodies of constant width with a class of support functions, so function defined on the unit circle, which satisfies, as we have seen, h of theta plus h of theta plus pi equals the diameter, the width. And moreover, we recognize support function of a convex set by this inequality constraints. The support function of a convex set is a function h which satisfies this differential inequality. So we work with support function, and more precisely what we do is to consider perturbation of the disk which are generated by a function of the shape of the form 1 plus epsilon phi. So 1 is the support function of the disk, of course, and we perturb it by a function phi which satisfies phi of theta plus pi equal to 0 in order not to change the diameter. You see that if epsilon is small enough, the convexity constraint h double prime plus h non-negative is automatically satisfied. And so as I already said, it consists in looking at perturbation driven by a phi whose even Fourier coefficients are all 0 in order to have this relation about phi. Then we compute first derivative. The first derivative is always 0 because the first derivative only involves the integral of odd coefficient of the series of the Fourier series. So the integral is 0. And so we are going to look at the second derivative for the simple eigenvalue. So here I give the proof for the case of simple eigenvalue, think to lambda 6, for example. The corresponding eigenvalue is a path 0 of the Bessel function G0. And so you end up with some complicated expression like that, but the not so complicated, actually, a simple expression like that with a polynomial in G0, which is given here. This is the polynomial. And when you compute this polynomial on the path 0 of G0, what you get is a number which is negative for p equals 2, 3, and so on. So what does it mean? It means that if you perform a perturbation driven just by A3, you consider a Fourier series with just one coefficient which is not 0, which is A3. For example, you take A3 is called 1. All the other Fourier coefficients has to be 0, and you are able to prove that the second derivative is strictly negative, proving that this shape is not a local minimum. For double eigenvalue, it's the same idea. It's much more complicated because the computation is much more involved. What you get in general for the first derivative is always 0. It's a multiple eigenvalue, so we have to deal with a derivative of multiple eigenvalue. With I claim that directional derivatives exist. They are all 0, so in that sense, this is a critical point. And when you look at the second derivative, the structure of the second derivative is as follows. So you have a second derivative which writes as some bilinear form L1 plus or minus absolute value of L2, in the sense that it provides an expansion of the k and k plus 1 eigenvalues as of omega epsilon as lambda, the double eigenvalue, plus epsilon squared times this second derivative, with the plus associated to lambda k plus 1 and the minus associated to lambda k. And then you have to analyze finally these terms in order to get the result I claimed about ranks, indexes for which it is not a local minimum and indexes for which it is a local minimum. I want to emphasize the fact that this notion of local minimum is a weak notion because I just proved that the second derivative is non-negative. It is not enough to claim that it is a local minimum. More precisely, so when you have a second derivative which is non-positive with the first derivative which is 0, it's not enough to claim that you have a minimum, of course. In principle, what you should need to prove is a stronger result. It is the fact that the second derivative is estimated from below by some norm of the perturbation. I refer to papers, to the PhD thesis of Marc Dambrine, or more recent paper by Dambrine and Lobolet, where all this stuff is explained in detail. And you see what is the relation between the norm you choose here and the local minimality. And of course, this is more difficult to get than the previous inequality. And in our case, the expression of the derivatives is so complicated that we try to prove such a lower bound, but it is really complicated. We succeeded for lambda 3, for example. We were able to prove that the second derivative of lambda 3 is estimated from below by a positive constant times the H1 norm of the perturbation. So in some sense, you get a local minimality in the class of H1 perturbation. Okay, so when you do some numerical simulation, so here I just put the interesting value. I mean, for the value of k, so k equal 1, we have already seen that the result is a disk. For k equal 2, 3, 4, 5, 7, 8, 11, 12, which are in my list of my theorem, the numerics confirm the local analysis in the sense that the disk seems to be the global minimizer for all these values. So here I present the minimizers we got numerically for the other indexes, lambda 6, lambda 9, lambda 10, and so on. So you have bodies of constant width. You can see that the width is the same in all directions. The domains seems to be regular. My picture is not very good, but the domain seems to be at least C2 regular. The curvature seems to be continuous. And you have something which is, we have not specific patterns to emphasize here. So if I want to state some open problem, some conjecture in that problem of minimizing lambda k with a diameter constraint, the first one could be, okay, can we prove that the disk is indeed a global minimizer for the list? Lambda 1 is known, lambda 2, lambda 3, lambda 4, lambda 5, lambda 7, lambda 8, and so on. It's probably a very difficult question. So, the regularity could be easier, I don't know. We know that the optimal domain is body of constant width. Can we prove that it is C2, for example, as we seems to see on the numerical simulation? And the last point about the multiplicity, because I will come back later for the Steklov problem about that question of multiplicity. For example, I will show you the table of multiplicity for the minimization of lambda k with a volume constraint. And what we see is that at the optimal domain, lambda k is always multiple for the Dirichlet eigenvalues with a volume constraint. Here, for the Dirichlet eigenvalue with a diameter constraint, we have not the same situation. What we see, but it's just numerics, we have seen that when the index k corresponds to a simple eigenvalue of the disk, so for example, k equals 6, it seems that the optimal domain has a simple eigenvalues. When k corresponds to a double eigenvalue of the disk, but when this is the lower index, it is still a simple eigenvalues. And when k corresponds to a double eigenvalue of the disk with a higher index, it seems to be a double eigenvalue. This is very strange because, as we have seen in the previous picture, these domains are not related to the disk, but the pattern of multiplicity seems to be related to the disk. So I have no explanation of that. Okay, so this is the end of the first part of my talk about Dirichlet eigenvalues. Now I am going to shift to Steklov eigenvalues. So I am looking at the Steklov problem on the domain omega. Laplacian of v is equal to 0, dv over dn is sigma v. And for example, for the ball, sigma, so as I mentioned previously, sigma 0 for me is equal to 0. So for the ball in Rn, the n first eigenvalue are equal to 1 over the radius of the ball. And then you get 2 over the radius, 3 over the radius, and so on. So for the Steklov eigenvalues, it's well known that it is not the minimization problem which is interesting because the infimum of the sigma k will always be 0. So the infimum of sigma k is not, it's a trivial problem in some sense. Whatever the constraint you put, actually. So we are interested in the maximization problem. So we want to maximize sigma k among domain in Rn with a diameter constant. I can put either equality or inequality, and if I put an inequality, it is in that sense because it's a maximization problem. It's a reverse that the previous case. Obviously, if you want to get rid of the constraint, you can. If you want to look at the unconstrained optimization problem, what you have to do is to multiply using the homogeneity of the eigenvalue. If you make a dilation, sigma k is divided by the ratio and the diameter is multiplied by the ratio. So this is a product diameter times sigma k, which is a scale invariant. And so these two problems are equivalent. And the second one, there's advantage in some sense to get rid of the constraint, and you can make perturbation in more simple way in particular. So these are this is the maximization problem I am interested in. So let me come back with other geometric constraint. With the volume constraint, it's a famous result by Freeman Brock that for sigma 1, the ball is the maximizer. It's not so complicated to prove because you just have to plug into the Rayleigh quotient the eigenfunction of the ball, which are the coordinate x1, x2, xn. And so you are led to prove geometric inequality involving the moment of inertia. And so you get this. The fact that this is a maximization problem, of course, makes things more, not easier, but more natural. You just have to choose a good test function in the Rayleigh quotient, and so you want to satisfy the orthogonality constraint with a constant and so on. When you look at the maximization with the perimeter constraint, it's known that the ball is not the maximizer. So for example, look at the survey paper by Alexandre and Yosif. When you dig a little hole inside the ball, you are able to increase the product perimeter times sigma 1. And this proves that the ring with a very small hole is better than the ball. And so the disk is not the maximizer in the class of any domain with a perimeter constraint. And actually it has been proved that by Jean, Misha, and Alexandre, that this problem with the perimeter constraint actually has no maximizer. When you restrict the class of domain, for example, to the class of simply connected plane domain, this is a very old result by Weinstock. It claims that the disk is indeed the maximizer with a perimeter constraint. And this has been recently generalized to any dimension by Bucur, Ferronenich, Ciambetti when you restrict it to convex domains. So the maximizer of sigma 1 with a perimeter constraint is a class of convex domains is the ball in any dimension. Okay. So in another paper, Doreen, Bucur, Giacomini, and Trevesky has proved this inequality for the product. We are interested in the product diameter times sigma k for any k. The product diameter times sigma k is estimated from above by a dimensional constant C of n times the index to the power 2 over n plus 1. So when you are interested in maximizing diameter times sigma k, it means that we try to, in some sense, to find the optimal constant in this inequality too. So it was one of the motivation of our work. A last remark before going to the result. For the Dirichlet eigenvalues, we were dealing with a minimization problem. And so we have seen that Faber-Crane inequality plus isoperimetric inequality implies the fact that the ball was the minimizer of lambda 1, because the isoperimetric inequality is in the good sense, and you have the result just by comparing ball of same perimeter, ball of same volume, and the Faber-Crane inequality. Here, we are dealing with a maximization problem. So this is a reverse. If you can prove that the ball maximizes your eigenvalues, sigma 1 or sigma k, with the diameter constraint, it will imply that the ball is also the maximizer with a volume constraint, because it is a maximization problem. So the inequality goes in the reverse sense. So in some sense, for me, the diameter constraint is stronger than the volume constraint, or even than the perimeter constraint, because it is also true for the perimeter constraint, at least in the class of convex domain. If the ball maximizes sigma k with a diameter constraint, it will also maximize sigma k with a perimeter constraint. Okay? At least in the class of convex domain for the perimeter, and in the general class for the diameter. So the diameter constraint is stronger than the volume or the perimeter constraint for the Steklov eigenvalue, because it is a maximization problem. For the Dirichlet eigenvalue, it was a reverse. The volume was stronger than the diameter of the perimeter. Okay. So first of all, the existence question. The first observation is the following. If you have a domain with holes, so for example, imagine you are in 2D and you have a non-simply connected domain, you have a domain with some holes inside. And what happens when you remove the holes, when you fill the holes? It's easy to see that doing that, you will increase the Rayleigh quotient, because you will both increase the numerator and decrease the denominator. And you remove parts inside, so the denominator will decrease, for example. So in some sense, we have for free in 2D that we can work in the class of simply connected domains, because otherwise it's not good to have holes. So it's a first observation, which is good in principle, but it's not so obvious to get something relevant with this property. We were not able to prove existence using this property of the maximizing sequence in some sense. So in higher dimension, I just claim that my domain, probably, if there is a maximizer, my domain has to be homeomorphic to the ball. It has no ball, no holes inside. So since we are not able to deal with general simply connected domain or general domain homeomorphic to the balls, we decided to work in the class of convex domains. So up to now, from now, we are going to consider convex sets in Rn. And my first result is an existence result in the class of convex domains. I claim that this maximization problem with a diameter constraint as a maximizer. So let me call it still one more time omega k star. I have a maximizer in this class of convex domains. So the proof is I just follow the classical method in calculus of variation. I consider maximizing sequence. I want to prove that it maximizing sequence converges to a convex domain open set. So like in my one of my previous proof, I need to prove that my maximizing sequence does not shrink to a flat convex set, because the diameter constraint do not prevent this kind of behavior. And for that purpose, we just wrote an estimate from above. So of course, it's from an intuitive point of view, it's more or less obvious. If you shrink to a flat domain, you expect the sigma k going to 0. But here in this proposition, we give a more quantitative flavor of this behavior of the Steklov eigenvalue when you collapse to a lower dimensional domain. What we prove is that for convex domain, you have an estimate from above of sigma k with a constant which is completely explicit. I can give you the value of this constant depending on n and k. It involves the Wallis integral and so on. Estimate from above involving the volume at the power 1 over n minus 1 and the diameter at the power 2n minus 1 over n minus 1. So in particular, it gives a quantitative flavor to what I claimed. If you fix the diameter and you imagine that your sequence of domain collapse, showing to a lower dimensional domain, you see that sigma k will go to 0 as the volume to the power 1 over n minus 1. So in particular, it cannot be a maximizing sequence because the maximizing sequence want to converge to the supremum, which is not 0. Then we will have compactness of this maximizing sequence because we are dealing with Hausdorff convergence into a domain. Since the diameter is fixed, you can suppose that all your domains are contained in a given ball. And so you just need now continuity or a Pearsonby continuity of your Steklov eigenvalue. And in a previous work, Benny Bogosel obtained such a continuity result when you have what we call an epsilon cone condition. So roughly speaking, for those who do not know this epsilon cone condition, it means that all your domains are uniformly Lipschitz. You can find a constant which is valid for all your sequence, Lipschitz constant describing the boundary of your domain. So epsilon cone condition is just a geometric translation of this uniform Lipschitz property. And so for your maximizing sequence with a diameter constraint, you can prove that there is an epsilon for which you have this epsilon cone condition. And in that context, you can prove that your sequence sigma k is fixed here, sigma k of omega n is my maximizing sequence, converge to sigma k of omega infinity being the limit of my sequence of omega n, and so you have existence. So like in the previous case, we are going to, we wonder whether the balls could be the maximizer of sigma k. And we have seen in my remark that if the ball is the maximizer for sigma k with a diameter constraint, it will also be the maximizer with a perimeter constraint in the class of convex domain, or the maximizer with a volume constraint. Since we have seen that the ball is a maximizer of sigma 1 with a volume constraint, and also the maximizer of sigma 1 with a perimeter constraint in the class of convex sets, but it's quite natural to ask whether the ball is also the maximizer, at least for sigma 1, with a diameter constraint, because it will be another proof of Brock result and Bucher-Feronenich-Trombetti result in that case. Unfortunately, or surprisingly, the ball is never a local maximizer, even for sigma 1. And to prove that, it's one more time a local analysis. We are going to take the ball to find a deformation of the ball which preserves the diameter, and such that the product, because we can look at the product, product diameter times sigma k, or diameter times sigma 1, increase under this perturbation. So for that purpose, we use the shape derivative of the Steklov eigenvalue. In the case of the ball, it's more or less, it's simple to write because the eigenfunction of the ball are explicitly known. So for example, here I wrote the shape derivative in the case of sigma 1, where we know that the eigenfunction are the coordinate. And since it is a multiple eigenvalue, we have to write n by n matrix, whose entries are precisely those numbers, where V is a perturbation I will consider on the boundary of the ball. Omega n is the volume of the unit ball. Delta gk is equal to 1 when g equals k. And so you have a general term of the matrix, which is this one. And to compute the shape derivative, so the perturbation of sigma 1, we need to look at the eigenvalues of the matrix. So we are now in finite dimension. Eigenvalues of the matrix whose entries are those numbers. And what we are going to do is to consider a particular deformation. So I work in spherical coordinates. I consider a perturbation which is driven by A2 and A4, so the cosine 2, the last angle, and cosine 4 times the last angle. So obviously this is not well defined when the angle phi n minus 1 is not defined, which occurs, for example, for the point 1, 0, 0, 0, for the point cosine phi 1, sine phi 1, 0, 0, 0. But these points are of zero superficial measure, so we can deal with them. And so looking at this perturbation, when we plug this perturbation into the formula which is above, we can see that most of the terms of the matrix are zero, except two terms. And what we are going to look at it is the submatrix, which is 2 by 2. And you can look at the eigenvalues of this submatrix, and you can prove that at least one of these eigenvalues is negative, proving that you can, positive, for example, proving that you can increase sigma 1 without, we have to pay attention to the diameter. And so we can increase the product diameter to sigma 1. And the idea which is underlying is that actually when we do that, finally the eigenvalue and the matrix which is above only sees the coefficient A2. The eigenvalue, the derivative of the eigenvalue does not see the coefficient A4, while the diameter sees both coefficients, A2 and A4. So by choosing in a correct way A2 and A4, we are able to make the product going in the good direction here. It is the meaning of my remark at the end. So let me come back to the multiplicity issue. Here I present the table of multiplicity for the Dirichlet. So I come back a little bit to the Dirichlet case. So you remember, so lambda I star will be the optimal value of lambda I with a volume constraint. So here I choose the volume equals to, should be 1, because I do not recognize a G01 square. So it is the area, I am in the plane, the area constraint is 1, and I give the value in the last column, which has the optimal value obtained for the shapes I showed on some slide at the beginning. And what I am interested in here is the multiplicity of this eigenvalue for the optimal shape. So of course, for lambda 1, we have seen that the disk is the solution and the lambda 1 is simple for the disk. But for all the other eigenvalues, as you can see, you have multiple eigenvalues. This is just numerics. We see numerically that these eigenvalues should be multiple. For lambda 2, we have two identical balls, and we have lambda 1 equals lambda 2. So we have a double eigenvalue. For lambda 3, we expect that the disk, sorry, it should be 2 here. In the plane, the disk has a double eigenvalue, lambda 2 equals lambda 3, and there is a mistake, this is a 2 here. Then for lambda 4, we can see that we have a triple eigenvalue. Lambda 2 equals lambda 3 equals lambda 4 in principle, and so on. So you see that you have always a multiple eigenvalue. More or less, it's increasing. The order of multiplicity is more or less increasing. It's not exactly increasing. When you go further in the list, you have sometimes a slight decrease, but it is always multiple. And so this is actually this is a conjecture. Prove that for this minimization problem, and actually for many other minimization or maximization problems for eigenvalues, prove that at the optimal domain, in the optimal situation, the eigenvalue wants to be multiple, right? So as I say, this is an open problem for the most famous case, the minimization of lambda k with a volume constraint. So here we were interested also in that question, and we were happy to prove, we are happy to be able to prove that here we have such a multiplicity result. And to my knowledge, it is probably the first time when we are able to get such a theoretical result about multiplicity. Obviously, we are obliged to put some assumptions. So these assumptions are, so we are in the plane, first of all. And this assumption is a regularity assumption. We are obliged to assume C3 regularity for the optimal domain because we are going to use the shape derivative. And for the Steklov eigenvalues, to be able to write shape derivative, we need at least C3 regularity of the domain. So we were able to do it in the general case without convexity constraint, because even if we are not able to prove existence, we can assume that there is existence. And we are able to prove that in that case, if there is existence, you have multiplicity. And also in the convex case, in the class of convex domains. So how does the proof work? Of course, we argue by contradiction. We assume that the eigenvalue is simple. Then, since it is simple, it's easier to write the shape derivative. We do not have to deal with this complicated matrix and so on. It is simple, so we write the shape derivative. Then we use the famous Rayleigh formula. For those who know it, it is also called the Poiseuille formula, which in 2D, this is the formula which is true for any C2 function, say. In 2D, it writes like that. And then you are going to play with this formula and with the shape derivative. So the shape derivative is nothing else than this relation between the tangential derivative of the eigenfunction, the eigenvalue, and the mean curvature, here the curvature because we are in the plane, the curvature. So this formula is just the optimality condition in some sense. It's the formula we get by using the fact that the shape derivative is 0. Of course, we have to deal with the diameter constraint. So we are going just first to look at points not saturating the diameter. For those points, we are able to make perturbation in any sense. And so the shape derivative is 0. And being 0, it implies this relation, that this relation holds on the boundary of the domain. And then we extend this relation also on points saturating the diameter. So just a simple analysis shows that this relation holds true actually on the whole domain. Then we use, as I said, we use this Rayleigh formula. We write the gradient as the sum of the tangential square plus normal square of the gradient. And so we integrate by parts in different senses. At the end, we end up with this relation, sigma k times the L2 norm of the shape of the eigenfunction to be 0, and we get the desired contradiction. And in the convex case, it's more complicated, but it works as well. Okay, so the C3 regularity is a little bit strong. As you are going to see in the numerical simulation, so I show you the numerical simulation immediately. Actually, what we see, so these are the optimal domain for sigma 1, sigma 2, sigma 3, sigma 4, 5, 6, 7. As you can see, the diameter constraint is achieved at 2 points. And at these 2 points, we have a corner. So in particular, we have not a C3 domain. We have a singular set at 2 points. At the other point, it seems to be regular. So I don't know if it is C3. I'm not able to see that on this picture, but it seems to be regular. So in particular, in my previous theorem, when I assumed C3, it's for sure too strong. But when I look at the proof more precisely, I do not really need C3. I need C3 most of the time in order to be able to write the shape derivative. But for example, in the picture I have, when I have only 2 singular points, it's okay. If I have C3 except at these points, it will be okay. I also need the curvature to be bounded, which seems to be the case in my picture, or at least bounded on the the curvature, no, it's not bounded at the extremities, but I need it to be bounded on the remaining part. And I need eigenfunction to be at least C1 regular, which could be true when I have a convex domain. So more precisely, the proof requires such assumption in order to get multiplicity. So coming back to the numerical result, I get this. And I will finish by that. You see that it seems that the asymptotic behavior, so even if asymptotic for k equals 7 is a little bit low, it seems that the sequence of domain converge not to a disk here, but to a segment. And that's interesting. And if you want to try to prove it, if we try to mimic the proof we did for the disk, so we take a sequence of optimal domains, it converges to an open set. So we prove it by contradiction. So assuming that it does not converge to a segment, we prove that it converges, it is a sequence of convex sets. So it has to converge to something. And if it is not a segment, it is an open set with the same diameter. And so first of all, we probably need a technical result to get a control of the difference. And then we choose something which looks like a segment, an ellipse, a very long ellipse, in order that its perimeter will be smaller than the perimeter of the limit. It's always possible. And we would like to finish by using Weil's law, because the Weil's law for Steklov eigenvalues, the Weil law which is known for a smooth domain, involve not the volume as in the Dirichlet case, but the perimeter. So in the same way, we will get a contradiction by using the fact that the perimeter goes in the wrong direction. And the most difficult problem in this proof is that, to my knowledge, the Weil's law for Steklov eigenvalues is known for smooth domains, but here I have no idea whether for example, my omega infinity would be smooth. So I cannot claim that my Weil's law for Steklov is true here, because it might happen that my domain is a polygon, for example, and we know that the Weil law for polygon is much more complicated. So this proof is not a proof. It's just a tentative, but I'm not able to prove that it is the same. So this is the end of my talk. Just to finish, I give you an exercise of inverse modeling. Inverse modeling means, okay, I give you a shape. Are you able to find the eigenvalue and possibly the constraint for which this shape is optimal? And this is my shape, which is, I'm very sorry for this joke, but everybody is concerned with this shape, so I wanted to put it on my slide. Thank you.
Thanks a lot, Antoine, for this presentation. If anybody has questions, you can either unmute yourself or ask them in chat, and I will relay them to Antoine.
I have a question and a comment. This is Josef speaking.
Yes, hello, Josef.
Yeah, so first of all, thanks a lot for a great talk. So my first comment is regarding your very last remark concerning the Weil law.
Yes.
So the Weil law, in fact, is known for piecewise C1 domains.
Okay.
So this is due to Agranovich, for instance. So I can send you a reference later. So if you are interested in just the main term, then piecewise C1 is enough. Yes. So actually, for polygons, you have much more refined results, which we have obtained recently. But piecewise C1 is true in general. So what is indeed not known, to my knowledge, is whether you have Weil law for Lipschitz domains.
Yeah.
So for Lipschitz domains, you know that the spectrum is discrete. But to my knowledge, and that was a question that I've heard from Agranovich many years ago, that there is a Weil law in that case. So probably there is one, but we don't know how to prove it. And a question that I have is, what about the Neumann case? So what is known as the Neumann case for isodiametric inequalities?
Actually, I don't know. I probably need a young student or a young collaborator to give.
But is there a particular reason you decided to look at the Steklov and not on Neumann?
Wait. Yeah. No, there is no. I don't remember if there was a particular reason. So the point is that so the collaborators you see, Abdelkader and Florent, arrived in École des Mines and they wanted to learn shape optimization. So I was trying to find a problem which seems to be tractable. And why Steklov? Probably because I just came back from Montreal.
No, I have. I certainly approve of the Steklov, right? So I was just curious. So you're saying that for Neumann there is not much is known.
No.
Thank you.
Are there any other questions or comments from Antoine?
I have a question. So I think in some problems on like maybe membranes or something, there were some maybe maximization problems, shape optimization, where there was kind of a mixed constraint which involved volume and surface area, maybe in dimension 3, but not sure what kind of eigenvalue it was, but so is it interesting to look at those eigenvalue at the extremal problems for such functionals?
So Dima, you think to both constraint, both volume and surface area together.
So it's more like a Robin. So it's maybe linear combination of the two. I have to remember, but I think maybe some, in like mathematical biology or in.
Yes, exactly. I was thinking to that because there is a famous geometric functional, which is a so-called Elfrich functional, looked by biologists to.
Right. So Helfrich is something, yes. Mm-hmm.
Yes, for which you need to put constraint on the volume, which is a volume of liquid inside your vesicle, and the surface, which is the volume of liquid between your bilayer. So biologists and mathematicians look at these two constraints for the Elfrich functional, which is related to the Vilmor functional.
Right, and there were some interesting shapes which were also either numerically or you just observe them, under a microscope, and they looked interesting, but not like it was not a ball. It was something. It was something else.
Not a ball, because in general, if you put your two constraints, the ball is no longer a competitor. Yes, there are many works in that direction. For eigenvalues, I just know the paper I mentioned by Vandenberg and Iversen, where they were minimizing lambda k with both constraints, and even existence it was not so clear. But I do not know any other motivation also to look at these two constraints together for eigenvalues.
Okay.
Thanks, Dima. Are there any other questions or comments? I'd have one myself in light of Yosef's comment. So you were saying that you don't actually need C3 for your proof, that probably that piecewise C3 or something like this would be enough.
Mm-hmm.
So do you have any sort of piecewise regularity results where you?
No, I'm not. We did not try. In general, regularity result for the optimum is a tough question. It's a difficult question. In particular, in the Steklov case, I do not know any of them in that spirit. Even for the Dirichlet case has been much more studied, but in the Dirichlet case, except the two shapes we know, lambda 1, lambda 2, there are no regularity results which are known. So it seems to be a very difficult task.
Mm-hmm.
So we did not try here. I have no really idea how to do that.
Mm-hmm. I think I did not realize exactly. I don't realize exactly how difficult regularity.
Yes, no, it is because the idea in general is to try to use techniques of the free boundary community, or Caffarelli and so on. And you have to start and to be able to write something which makes the problem look like a free boundary problem, and to study it using a monotonicity formula and so on. So this is a very difficult task, according to me.
Okay, that makes sense. So any other questions for Antoine?
I have a question about numerical for Steklov, I guess, your second numerical pictures. So could you please go there? Oh yeah, this one. So this is for Steklov, right?
Yes.
So do you think it is getting thinner like this, thin long, because of the Neumann boundary condition?
I think it's become thinner, at least it is what we observe, and this is why we try to prove that it converges to a segment with exactly the segment of diameter d. We try to prove it, but we are not able, as I showed. But yes, numerically we observe this behavior, and it is very in contrast with the same maximization problem with the volume constraint. So some people, including Benny Bogosel and other people, did this numerical investigation with a volume constraint, and what you get is something which seems more and more close to the ball, with a tiny oscillation on the boundary and very regular oscillation, but it is very close to the ball. And here you have something very, very different in that case.
So the oscillations on the boundary, that's for Dirichlet case, right?
No, this is for Steklov.
But
when you consider an area constraint instead of a diameter constraint, you have something which looks like, I have no picture here, but you have something which looks like a disk with a very regular small oscillation on the boundary when you maximize sigma k with a constraint on the area of the domain.
So right now here, the first picture is constant width, right?
No, because not exactly. It's not a constant width. The diameter is not the same. For example, in that direction, you have not the same width that in that direction.
Okay, so that one is from the calculation, or what you draw? Is that it? Is that from the calculation, the shape that you have?
Sorry, I do not get what you ask.
Oh, is the shape for the first one, is that coming from calculations or?
Yes.
Oh,
all of these are coming from calculation. Yes.
Oh, okay, I see. Because what I've been thinking is for your previous simulation, like the numerical results for the Dirichlet case.
Yes.
There are disks in between, but between disks we have constant width shapes.
Yes.
So the first eigenvalues, they repeat twice. So for every twice we have the constant width shape between that. So yeah. I haven't computed higher eigenvalues for the disk, but for the square, it repeats more. So some eigenvalues repeat more than 2. So sometimes we have 4, sometimes we have more than that. So like my question was like, do you think that there's some kind of pulsing behavior between that, and it becomes it becomes a disk, and then it comes back, and then it's kind of like constant with, like, polygonal approximation for the disk. So I was thinking like maybe for the middle things, then it is kind of happening like polygonal shapes approaching disk and becomes a disk, and then come back, and then it becomes a disk. I don't know. This is just.
In principle, my theoretical result answer partly to your question, because I know that after the rank 50, I never meet the disk again. I always get a body of constant width different from the disk. So this is theoretical. But we can go on the discussion probably after that or by email if you want.
This sounds good. Thank you so much. I appreciate it.
You're welcome.
Right. So as time comes to an end, we will thank Antoine for this talk again. We can all join next week for the presentation by Christiane Tretter, who will talk to us about spectral problems on star graphs. Now, for people who are on the old continent, the talk next week will be 1 hour earlier than it usually is. This is due to the fact that we go back to winter time 1 week earlier than in North America. So we have no choice but to change the time somewhere. So we will have the talks 1 hour earlier next week for those of us who are in Europe or, and I guess the UK. Well, see you next week. And thanks again, Antoine.
Thank
Bye.
you.